Bangalore Theory Seminar Series. This week, we are excited to have Professor Thomas Kesselheim as our guest speaker. Professor Thomas is a professor at the Institute of Computer Science at the University of Bonn. His research interests lie in the area of approximation algorithms, online algorithms, and algorithmic game theory. His work on online independent sets beyond the worst case, secretaries, puppets, and periods won the Best Paper Award at ICAP 2014, and his work improved algorithms for latency minimization in wireless networks. Also was the recipient of Best Paper Award at ICAP 2009. Today, he has very kindly agreed to give a talk titled Online and Bandit Algorithms Beyond LP Norms. So let's welcome Professor Thomas and all yours, Professor.
Yeah, thank you very much for inviting me. I'm excited to give this talk on joint work with Marco Molinaro and Sahil Singla, which appeared in SODA this year. And as you were saying, the title is Online and Bandit Algorithms Beyond LP Norms. The problem I'd like to focus my talk on is a problem I think many of us know and love, which is online load balancing. It's a very simple problem that has been studied for a long time. What's the problem? We have D machines, and in each step, one job arrives, and we can choose which machine to process this job on. So these are unrelated machines. We get to see how long it would take for this job on each of these machines. And then we just choose which machine to assign it to, and then we get to see the next job. And then again, we can decide what machine to process it on. So quick example here, we might have this first job. We could process it on the first, second, or third machine. Maybe let's choose the first machine, and then the second job arrives. And we could again process it on the first, second, or third machine. Maybe we again choose the first machine. What's our objective? Well, the traditional objective is to minimize the make span. What's the make span? That's the maximum load of any machine. The load of a machine, that's just the sum of the processing times that we are of the jobs that we're assigning to that machine. So in other words, we will get this load vector where this lambda subscript I superscript t is then the sum of the processing times of the jobs we assigned to machine 1 or 2 or whatever. And the make span objective, that would be nothing but minimizing the L infinity norm of this final load vector. And this problem has been studied, and it was already, at least the make span version of it was kind of solved 30 years ago by giving an O of log D competitive algorithm for the L infinity norm, as I was saying. So just that we're on the same page, this means that the make span of the algorithm is no more than O of log D times the load of an optimal offline solution, times the make span of an optimal offline solution. And only shortly after, this was generalized to LP norms, and then what you get is an O of min of P and log D competitive algorithm for arbitrary LP norms, so for any P of at least 1. Good. So these are actually both tied. So apart from the constant factors, there's nothing else to be done here. But the natural question that this raises is, what about more general norms?
So Thomas, a quick question.
What if you go beyond LP norms? Yes.
So no preemption and it's integral assignment. You're going to just focus on that.
I'm assigning the jobs integrally, exactly, and I cannot. So my decisions are irrevocable. Once I assign a machine, once I assign a job, I cannot reassign it. Preemption is actually, sometimes in these online scheduling problems, you'll have questions of preemption, meaning that you started a job and then you might want to change things. That is actually not so much of a question here, because eventually all that matters is kind of the final load vector. So there's no real notion of time in that, or the notion of time that we have in terms of these timestamps that is unrelated to the processing times. I might want to stress on that.
Okay. And you know the number of jobs upfront, or that's not a requirement?
I don't know actually the number of jobs beforehand. The thing is that won't actually help. Knowing the number of jobs beforehand wouldn't actually help me because
Right. Zero.
well,
Yeah.
I could, exactly as you're saying, this could be eventually I could have like 0 jobs at the end, so I could artificially inflate the number of jobs. So, and I won't need that knowledge.
Okay. And this is competitive. Like, don't you need like an asymptotic version of competitive ratio? This is the standard.
There's no there's nothing asymptotic here. Well, except for that I'm hiding the constant factors, but it's not that opt has to be large or so. There are also results for this problem where opt is large, but at least when you have the worst case model, that doesn't actually make a difference. So opt can be arbitrary.
Great, thanks.
Sure. Yeah, please feel free to interrupt me at any time. That's actually why it's great that I'm giving this live talk and not just a recording. Cool. So this is our problem. And what we are now interested in is what about more general norms beyond, well, the L infinity norm or slight generalization to LP norms. So what would that mean? Well, what is a general norm? I hope you recall. By the way, because I'm only worried about non-negative vectors here, I'm leaving out the absolute value here. So what would be a general norm? This would mean this function would be homogeneous. It would fulfill a triangle inequality and would be 0 exactly for the 0 vector. All LP norms fulfill this, but LP norms fulfill even more things. Namely, they are monotone, meaning that if you increase any coordinate, then the value of the norm will never decrease, which certainly makes sense in this application of load balancing. And then they are also symmetric, which means they are invariant to renaming the coordinates. So if you apply any permutation to the coordinates, the value of the norm remains the same. LP norms fulfill all these 3 conditions, or well, they are norms which are also monotone and symmetric, but there are also other examples. Like LP norms can be generalized to so-called Ullage norms. They are still monotone and symmetric. Or there are other examples like top K norms. What is a top K norm? There I just take the sum over the K largest components of my vector. So the top 1 norm, that's exactly the largest entry, which is nothing but the L infinity norm. The top D norm, if I have D coordinates, is nothing but the sum of all coordinates. So that's the L1 norm. But the top 2 norm would, for example, just take the sum of the 2 largest entries. Those can also be generalized to so-called ordered norms. And nice thing about monotone symmetric norms is that also if you take non-negative linear combinations, compositions, or norms of sorted vectors, this will give you again monotone symmetric norms. And this is why these monotone symmetric norms have been studied recently in offline problems. Here mentioning a few papers here, but we are now interested in what we can do in these online problems, in particular in our online load balancing problem, which I'm considering here as the main problem for this talk. So for this online load balancing problem, we can show that for every monotone symmetric norm, there's an O of log squared D competitive algorithm. Recall that for the L infinity norm, which is a special case of this, log D was optimal, was tight. So we're at least close to what we could hope to get for every monotone symmetric norm. We don't actually know whether log squared D or log D would be the right answer for this problem, but at least we get kind of close to this.
So one question.
Yeah, sure.
So is there a motivation for monotone symmetric norm? Like L infinity is quite natural, but in practice, is there any motivation?
Well, I do feel that, or what motivates me always is these top K norms that I would be, so what, there was a motivation, for example, for these LP norms to say, well, and I don't recall how they actually motivate this. They did this like 30 years ago. The general motivation is that I'm interested in more than just the maximum load. And I think top K norms are also a very interesting way to actually capture this. That I'm, at least in this load balancing problem, that I'm interested in more than just the maximum load of any machine, but also, well, I might have something like the load of the maximum, the highest load plus a half times the second highest load, something like this. I can all capture by these monotone symmetric norms. So this is also kind of relaxing this objective. But I'm not really an expert in what these things are used for in practice, but I've been told that there are actually interesting, that there are applications where you want to have some other kinds of norms.
Okay, thank you.
Sure.
Yeah, so like collisions are sort of counted. So like one way is to like look at them as like welfare or like cost functions on this D machines, and you're looking at sort of richer class of cost functions. It's like a sort of welfarist view on the. I mean, one way is to kind of see that like L2, for example, is a fairer load balance than.
Right.
So, and also like in databases and all, like this counts like collisions of sorts. So like the load,
cool.
yeah. So yeah, but
right.
Those are sort of interpretations of norms that you can. I mean, think of the D machines as individuals or agents, and then like the fairness and other sort of things would correspond to these sorts of things.
Very good point. Yeah, that's like getting fairness between machines is certainly one objective that's captured by some other norms. Yeah.
Yeah. So the top K would be like the K worst of machines are still like. I mean, the lower quantile of that population is still not overburdened.
Right.
That's
good. Yeah. So regardless of the motivation, this is, I think, also just theoretically a very interesting problem. I'll tell you a bit more about other norms at the very end, but which are not monotone symmetric or not symmetric for that matter. But let's first just take this problem for granted, and we now want to discuss how can we actually get this O of log squared D competitive algorithm for monotone symmetric norms. And the way we do this is actually interesting, I feel, because this also can be applied to other problems. Namely, we show two things. The first thing that we show is that if a monotone norm admits a gradient stable approximation with error alpha comma gamma, there is an O of alpha plus gamma competitive algorithm for online load balancing. I have not yet told you what a gradient stable approximation is. I'll do that in a second. But this tells you that if this gradient stable approximation exists, then this gives you immediately your algorithm for this online load balancing. And the second ingredient, you might guess, is that every monotone symmetric norm admits such a gradient stable approximation. Namely, these errors are alpha is in the order of log D, gamma is in the order of log squared D. And if you then combine these two bullet points, then immediately you get your O of log squared D competitive algorithm. We also have more results for other problems, including, for example, adversarial bandits with knapsacks, and we also have results for other norms. I hope I'll come to this at the very end of my talk, but for the time being, I'd like to spend most of my time on these two bullet points, namely, first of all, what is a gradient stable approximation of a norm? And then how do we get a gradient stable approximation of any monotone symmetric norm? Good, but what is a gradient stable approximation of a norm? You might have seen one example of a gradient stable approximation of a norm, which is the well-known softmax function. This approximates the L infinity norm. It's defined this way. This epsilon, this is a parameter which controls how well you approximate the L infinity norm. Namely, here you'll see the approximation guarantee. Your softmax is always at least the L infinity norm, but it is also upper bounded by the L infinity norm plus log d over epsilon. So if you make epsilon larger and larger, asymptotically, you'll actually reach the L infinity norm. But a smaller epsilon does have some advantages, and that's what you can see here in this contour plot. So these blue lines, those are the level sets of the L infinity norm, just as you would expect them to be. And these red lines, those are the level sets of the softmax. And what you immediately see is that the softmax, well, that looks much smoother, that's much rounder. And this is exactly the property that we exploit, which we formalize or which we generalize and which we then exploit. Namely, what would we like to have for a general approximation, or for if we're given any other norm? What two properties would we like to have if we then find a function, or we will then be given any other norm, and what we're looking for is a function psi which fulfills, well, exactly these two things. The one thing is this function psi should then approximate that other norm, meaning it should be at least the norm, but it should be no more than alpha times the norm plus gamma over epsilon. So that's just generalizing this approximation property of the softmax, where alpha would be 1 and gamma would be ln d for the softmax. That's the one property. And then the other property that we would like to have is that this function is supposed to be gradient stable. What does this gradient stability mean? Maybe let's first look at this in the case of the softmax. Let's look at the gradient of the softmax. And the gradient, I hope you recall, is always orthogonal to the level sets. So if we're if we move along such a line, then here it always points to the top. So it's the vector 0, 1. But then, as soon as if we move a little further to the right, as soon as we approach such a corner, then suddenly the gradient changes. So the gradient of the L infinity norm changes drastically. It changes from being 0, 1 to 1, 0, which means that the second derivative drops down from 1 to 0. For the softmax, something like this will never happen. And this is exactly what we'll the property that we require for the gradient to hold for our approximation. Namely, we ask that if you take the gradient at some point x plus y, this should be lower bounded by the gradient at the point x times some error term. And namely, this error term is e to the minus epsilon times the norm of the shift. So we shift it by y. This is the norm of the shift minus delta, where delta is again another parameter that we allow our norm approximation to have. So delta would simply be 0 in the case of the softmax, but in our norm approximation, this will be something greater than 0, but we can choose this delta actually, and it will influence the approximation guarantee of the norm. These are the two properties that, for example, the softmax fulfills with some, I told you alpha is 1, gamma is ln d, delta is 0. And then we can use this for any other norm. If we have such a gradient stable norm approximation, we can use it to then define a very simple algorithm for online load balancing. Yeah, sure.
So this gradient stability does not follow, I'm guessing, from like a Lipschitz condition on the gradient.
No. The good point. There are many similar notions in the literature, which are wouldn't even know where to start. I think we have one page in our paper where we discuss all of these different notions that are there in the literature, but they're all different. So what is important here is, for example, that this is only multiplicative, the error. Usually in other examples, you'll see that you'll have an additive error here in by how much the gradient may change. Because then this is actually easier to show, because you would need this. You could talk about the Hessian, so the second derivative, that then would give you these additive errors, but we actually insist here on this multiplicative error because ultimately we will need the multiplicative guarantee.
And you actually do need it for y's that are large now, in the sense that you don't want, like if y and epsilon were like, I mean, if these three parameters in the exponent were small, you could probably write like a linear or a quadratic Taylor expansion for exponent, and but that won't help you. Like like this. I mean, I shouldn't be thinking of y as a small step. Rather, you really want it for even a large norm y.
That's a good question. I think this in our analysis, this exponent here will always be bounded by a constant. So maybe also you could approximate the exponential function by some polynomial. It just turns out to be easier to work with, but I think that would make a huge difference.
Yeah, it just aesthetically, like that might resemble something that's a bit more familiar. Like it's a norm of y times rather than the exponent. But I kind of, probably the derivation is what speaks more here than the aesthetics.
Right. So yeah, exactly. For our purposes, this was the easiest to work with, but yeah, in the regime we're interested in, you could probably also write down something similar, like 1 minus epsilon times something would probably still be kind of similar.
Thanks.
Sure. Good. So let's now assume we have a norm which admits such a function psi which fulfills these properties. How can we, what kind of an algorithm can we define? Well, there's just the natural algorithm, which is this, the algorithm to use this to do greedy with respect to this psi function. So what do? You always choose the option to schedule a job that minimizes the increase of your norm approximation. This is the smooth greedy algorithm, and so the greedy algorithm would be just choose the option that minimizes the increase of the norm, which would not work, by the way. This is what people already realized like 30 years ago, but this algorithm does work. At least if your norm fulfills this, if your norm approximation fulfills this gradient stability. Namely, what you can show, and what I will show you in the following is how you do that, is that if you choose this epsilon to be in the order of 1 over opt, and this delta to be some small constant, then the norm of your of the solution of your algorithm, of the load vector of your algorithm, will be bounded by O of alpha plus gamma times the norm of the optimal offline solution. Good.
So one more.
Yeah.
One question. So is in a way your algorithm a generalization of the Aspiness algorithm? Because I think for infinity norm they use some kind of softmax function and trying to do that. I see.
Right. So this is what people did like 30 years ago, was doing exactly this with a softmax. But what I'll be showing you now is that actually, and for what I'm showing you on the next slides, it's fine to just think of psi being exactly the softmax, but then let's see what properties of the softmax we're actually using, that we're not actually using the precise formula, but what properties, and I claim that this gradient stability is actually all we need.
Thanks.
Besides the fact that this approximates our norm. Good. So what follows from this gradient stability is this following approximate supermodularity. So this is just the definition of gradient stability. I told you that the gradient should never drop in any component true drastically if you shift by a bit. And this implies this approximate supermodularity. And let's first maybe look at this picture down here. So what am I asking? I'm talking about the increase of my norm approximation when I move from some x to some x plus z. By how much does the norm approximation, the function psi, by how much does it increase? Well, that's just something. And compare this to by how much does it increase if I move from x plus y to x plus y plus z. So I just shifted everything by y. And then this approximate supermodularity tells me, well, the increase of the psi from this x plus y to x plus y plus z is lower bounded by the increase from x to x plus z. And what you get here is exactly the same error term, which is, well, because this is a straightforward conclusion from gradient stability. So the increase that you'll be getting is lower bounded by this e to the minus epsilon times norm of y minus delta times the norm times the increase when only increasing x by z. So this we call approximate supermodularity because this looks very much like supermodularity of set functions, because if you add more from where you're starting, then the increase should only be larger. Which, by the way, is a little surprising that this holds because your function is actually convex. So you'd rather think of you would rather think of this being kind of submodular, but because we have this gradient stability, we also have this property. And this is exactly what we can use in order to analyze the smooth greedy algorithm. Let me first give you an idea of how you would do this pictorially. So what would this look like? So suppose we just have two machines, and we now want to see by how does the load vector increase over time. And we start with the first job, and maybe our algorithm puts it on the first machine, but on the second machine, but the opt, because it knows which jobs will come in the future, puts it on the first machine. But our algorithm decides to put it on the second machine because this is locally better in terms of the increase of psi. And then we get the second job. And well, what we could in principle do is we could do what with this job, what the optimum does with this job. Although the optimum is, of course, it's the load vector of the optimum is, of course, down here at this point because it put the first job on the first machine, but still we could do the same thing with the job that the optimum does with this job. But locally, maybe it's better to put it on the first machine than to do what the optimum is doing. And then the third job, again, we could put it, we could do what our algorithm does, which is in terms of the increase of psi is at least as good as what the optimum does. So then the sum of these blue arrows, this is exactly the load of our algorithm. The load of the opt, that would be what you would be getting if you added up all these red arrows, which we don't yet see in this picture. But in order to compare the lengths of these blue vectors, or the norm of these blue vectors, of these added blue vectors to the norm of these added red vectors, we rearrange this picture. Namely, what I can do is I can shift these arrows to align. So let's just pretend we first do what opt does with the first job, and then we also do what the algorithm is doing with this job. And then for the second job, we do first what opt does with this job, and then we also do what the algorithm does with this job. And similarly for the third job. Then this final load vector, that's just the sum of these two load vectors. And the point is that what I did from going from this left picture to this right picture was actually just shifting these arrows, but I never shifted them by really a lot. This was always bounded by the final load of opt when getting from here to here, because, well, every shift is actually upper bounded by just the overall length of these red vectors. And then in this shift, I can use this approximate supermodularity. Let's do this a little more formally. What do we do? So let's see, how does the norm approximation increase over time? So what's the final norm approximation? How much does the norm approximation increase from the start to the final load vector? And this we can actually write as a telescoping sum. So just take the sum over all timestamps by how much does the load vector increase in the tth timestamp. And then we know that for each of these terms, we know, okay, this is no more than if we did what the optimum does with this job. So I multiplied this by 2, so I keep one term here for what the algorithm does, and then I'll also have this one term for what the optimum does with this job. And now I apply approximate supermodularity. I shift these. First thing, I shift by the load incurred by the opt until step t-1. The second, I shift by the load incurred by the opt until step t, and this gives me this error term. And then, why did I do this? Well, because this is again a telescoping sum. So what this is exactly the increase of the load from the zero vector to the sum of the alg plus the opt load vector times this error term, which I'm getting from gradient stability, respectively, from approximate supermodularity. And if I now choose this epsilon to be 1/5 opt and delta to be a fifth, then this error term is no more than 3/2, which then means I can, using also subadditivity here of my function psi, I get this. I get that 1/2 times the final value of my norm approximation is no more than 3/2 times the final value of the norm approximation for opt plus 1/2 times the norm approximation for the all zero vector. Now we are almost done. We just multiply this by 2. We get to this inequality here, and then we only use the approximation guarantee of the norm approximation. So this on the left hand side is at least alg. On the right hand side, this is at most. Just do the math, and you see, okay, this is at most some O of alpha plus gamma times opt. And so, actually, by only using these two properties, namely that we have this approximation of our norm with multiplicative error alpha, additive error gamma over epsilon, and the fact that we have this gradient stability, which implied this approximate supermodularity, we immediately get this O of alpha plus gamma competitiveness. And this is actually all we need. So this tells us that in order to get any good algorithm, all we would have to do now is to find a good approximation of any other norm besides the softmax, which we already know does exist. Before I get there, let me first ask if there are any further questions right now.
So you use this approximation right at the end, like in the sense that the
yeah. Okay. So
and
this is only happening here what in these two steps. So this one step is using the fact that the norm approximation is always at least the norm, and here this other step is using that the norm approximation is always upper bounded by in terms of the norm with these two kinds of errors.
But you're actually getting a very nice guarantee in terms of p, like it's just a constant, like 3. Okay.
Yeah. I have a question. So did you use this monotone property and there was this other property that it is invariant to the change of coordinate. Did you use them?
No. So far, this is I didn't. I'm not sure if I used monotonicity anywhere. Maybe I did. I certainly did not need that this is a symmetric norm. So this I'll be only using now in order to show that there exists such a function psi. But in general, and for all I know, every monotone norm or might admit such a gradient stable approximation, not only symmetric ones, but for all I know, this might work for any possible norm. I just wouldn't know how to do what I'm about to do in the second half now.
Maybe like a pedantic one. So you do need knowledge of opt to set epsilon, but maybe a doubling trick.
I need knowledge of opt, so I'll have to do some doubling trick. But that's just what people did like already 30 years ago. I think you'll have to do this even for the softmax. So
sure.
Good. So that's the first part. Now the second part is, as I was mentioning, which norms admit such gradient stable approximations? And what we show is that actually every monotone symmetric norm admits such a gradient stable approximation. So once again, this is what we want to do, is we want to find we're given any monotone symmetric norm, we want to find a function psi, which fulfills these two properties, that this is this approximates the norm, and that this fulfills this gradient stability. What can you do to get there? There are these three main steps. The first and the last one are not so super exciting. I think the second one is the most exciting one, but let's go through them one by one. The first thing is to approximate your norm by top k norms. Then you give a gradient stable approximation of top k norms, and then you show that this gradient stability is kind of preserved under composition of norms. So let's first talk about this first and this third step. Why is it enough to only consider top k norms? This is what people have observed before, that every norm can be and there we need the symmetry of the norm. Every symmetric norm can be approximated by as follows. It can be approximated by a norm which is just a maximum or a weighted maximum of top k norms. So this is I'm defining this other norm here, which is, well, even I take only top k norms where k is a power of 2, and then I have coefficients which are just some non-negative numbers. That's actually not so super difficult to see if you know a little about norms, namely that a norm you can always write as a maximum over dot products of vectors coming from some set W with a vector whose norm you want to bound, and then you can just rewrite this, and well, there's and there in this step you actually use the symmetry, because that means that this set W also has to be symmetric. So every permutation of vector, if a vector is contained in a set W, every permutation of this vector has to also be contained in that set. So this is why you can approximate any norm by by this maximum over top k norms. And then what you want to do is, well, given that you know that this is a maximum over these weighted top k norms, what you do is, well, you replace this maximum by the softmax, and then you replace each individual norm by each individual top k norm by its approximation. And then what we'll be showing, or what I'll be talking about in a second, is why this how you approximate these top K norms so that that you have gradient stability. And then what you still have to verify is that also this composition that you're getting here, this is again gradient stable. But the interesting part, at least for me, the most interesting thing that I'd like to give you a little more details about is how do you actually approximate a top K norm so that you get a gradient stable approximation. And how would we do that? So let's maybe spend some time thinking about what is a top K norm? A top K norm, that's just the sum of the K largest components of a vector. And what's its gradient? Well, the partial derivatives are actually quite easy. Those are 1 if and only if this component is among the K largest, and otherwise it's 0. So that's exactly what we saw for the L infinity norm, which is the top 1 norm. Now, how do you get from there to something which does not have these effects where components change drastically, which will happen here because this will drop from 1 to 0 immediately? Well, the first thing that you might do is exactly what I was saying, is you might want to use the norm directly. And then you see, okay, this is exactly what we had at the very beginning of the talk. Namely, if you take the gradient at epsilon and then 0, then the first partial derivative is 1, whereas then if you increase every coordinate except for the first one by 2 epsilon, then the first partial derivative drops from 1 to 0, and this is exactly what you don't want to have for gradient stability. The next thing that you might want to do, or maybe not the next, but something else you might want to do, is you could take the top K norm for, well, now a random K. So let capital K be some random variable, then you might say your approximation is the expectation of the top capital K norm. But that still won't work because of the exact same counterexample. Second approach, introduce some random noise. So your norm approximation is the expectation of the top K norm of X plus some random vector, but that usually won't work either. This is an example I could tell you, but maybe we don't even have to go through this. I can just tell you, okay, this doesn't work either. It's a more complicated example, but still the thing is, it would work if this noise was huge. If this noise was huge, then this would work, but then our norm approximation becomes too bad, because then, well, that's maybe not so much a surprise. If you add some very large noise, then of course you don't actually have at all the value of psi isn't actually doesn't depend too much on X anymore at all. Good. So those are sure.
Question. Yeah, so I'm wondering, like, I kind of see the counterexamples, like the sort of non-examples here, but I'm wondering, like, are they? I mean, are the pathologies confined to the origin? As in, like, if X is large enough, then you can do something. So I'm just wondering, like, for problem instances where you have a guarantee that all the machines would be loaded enough.
Good point. And I think this second approach is already talking about this, because this happens always. What goes wrong is always kind of close to the origin. And as you move away from the origin, things become nicer. And this is exactly the point I was trying to make. Namely, if you add a large random noise, this has a very similar effect as moving away from the origin. Or what I couldn't, maybe this similar thing would be introducing assumptions that you are that you're far away from the origin. I don't really know, but generally yes. So also, if you think about L2 norms or so, then only close to the origin, you have these weird effects. And as you move away from the origin, this doesn't happen anymore.
Yeah, like the Lipschitzness of square root x, for example.
Yeah.
Goes to 0. Yeah.
Good. But my point was that, okay, the second attempt is kind of trying exactly this, is trying to move away from the origin and to hope then, okay, that everything becomes nice. But the thing is, you have to move away too far from the origin in order for this to become gradient stable for our, or to have enough gradient stability for our purposes, which then makes the approximation too bad. But the amazing thing is that if you combine this with this first approach of choosing a random k, then this works. So what we do is we choose our norm approximation to be proportional to the expectation of the norm, of the top capital K norm, where this capital K is drawn from a geometric distribution. So its mean is exactly our small k. And this noise, this is drawn from an exponential distribution, and this becomes smaller as k increases. And then you can actually see that with this, you will get a constant multiplicative error and an additive log d error, and you'll have this gradient stability. And this is the way you do this is you actually write down the all partial derivatives, which you can do quite explicitly. If you once you have the formulas, you can write down these formulas for the partial derivatives quite explicitly. And then you can verify, oh, they fulfill this gradient stability. One minor thing. Yeah.
One quick question. Is there an intuition how you came up with this geometric and exponential? Why good question. Why would I take geometric and exponential distributions? I think I'm not sure if they are the only choices you could use, but they are extremely easy to work with because they are memoryless. So, and then this makes all your calculations easier in terms of well, maybe let's quickly go back to what was the gradient of the top k norm. This was 1 if it is among the k largest component, otherwise it's 0. And then you ask, okay, if we didn't have a random noise here, what would be happening is with this random k, for example, this is now the question, is it among then the gradient becomes what's the probability that you're among the top capital K entries. And then this is easier because this if you shift by one, if you increase if in the ordering of the coordinates you increase by 1 or you decrease by 1, that is bounded and is always bounded by the same because we have a geometric distribution. In principle, you could do similar calculations, I guess, also for other kinds of distributions, but this seems to be, at least I felt those were the most convenient to work with for these calculations. Good. Yeah, I wasn't completely honest here. Of course, we need this epsilon and delta because we wanted those to be small, and then you have to, these distributions become even a little more complicated. You have to introduce your epsilon and delta, but morally that's just the same. And then you get exactly the kinds of guarantees that we wanted. So the first one looks very similar to what we had for the softmax, except for that here we now have a constant which is strictly larger than 1, which depends on this delta. And yeah, here we also have the delta, but that is about the difference. The error term here is actually the same. So the additive error is the same. And then we see, okay, with this alpha being a constant, this alpha is a constant, this gamma is O of log D. So actually for every top K norm, we would get an O of log D competitive algorithm. And with this reduction to top K norms of all monotone symmetric norms, we would get this O of log squared D competitive algorithm because we lose exactly this further log D factor from the reduction I was showing before.
Hey, Thomas, can I ask a quick question slightly? So this is great. But I was just wondering, how do you actually find the tangent conjugate? If you go back, you started with this conjugate definition of the norm, which is that you look at it as a maximization problem over this dual set W. But it's not obvious to me. So you're assuming that the norm is given in terms of this W, rather because how do you find these? Good. Because once you have these W's, only then can you sort of start and
good question. Yeah. So I wasn't talking at all about computation so far. I was only saying, well, this thing exists. And we also, but that's also something we mentioned in our paper. I don't have any slides for this right now. But yeah, how do you compute these things? And this is what people already did in these offline algorithms for norm problems. That then what you can do is you can actually, or what's your assumption? The assumption is actually that you have a ball optimization oracle, which means that if I remember this correctly, for any x, you can find the W that is the argmax of this. And then you can use this to actually discretize your set W. You can discretize this in arbitrary precision. And then you can actually get a polynomial. So you can think of this set W just being polynomial size. And if you, then you're golden. When this W is just polynomial size, then you can do all these things in polynomial time.
Okay, yeah.
Good. So, yeah, this is it for online load balancing. I hope I gave you an idea of what the main ingredients are for that. Let me give you a rough idea of what else we have in our papers. So we can also apply our techniques to bandits with knapsacks or to the adversarial version of bandits with knapsacks. What's that problem? There are k-fixed actions, and in each timestamp, you can choose one of the k actions. You will receive a reward, which depends on which action you chose, and you will incur a cost vector, which is defined by some cost matrix. But the interesting thing is only then you get to know your reward and your this vector cost that you incur only after you make your choice. And your goal is now to maximize your reward subject to the constraint that the sum of these cost vectors is no more than some budget. And via our techniques, combining it with actually techniques Sahil and I developed in a paper which we published in Code 2020, using exactly this approximate supermodularity, and then also an approximate converse of Jensen's inequality, which also follows from gradient stability, we can show that there's an O of log squared D competitive algorithm for this problem for all monotone symmetric norms. So here now your norm actually shows up as the constraints. Here actually this notion of competitive ratio is asymptotically. So here you assume your time horizon to be large in order, because you also have some additive regret terms, which you cannot avoid in this problem. But generally this generalizes what for example happened in this Imorlica et al. Paper. Well, it improves and generalizes what happened in this Imorlica et al. Paper to constraints that are given by some arbitrary monotone symmetric norms. But we can also go beyond monotone symmetric norms with our machinery. For example, what we can study is online vector scheduling. That's a problem.
One question.
Yep, sure.
In the previous slide,
yep.
the norm you have on the budget constraint, but if you do something on the reward part as well, so you take a norm of the reward, then do you get something there? So even without the budget, the general vanilla problem of Bandits?
That's an excellent question. I don't really have a good answer to yet, because what you want to do here is, of course, the objective would be is a maximization objective, and maximizing the maximum, I don't think you would usually want to do. What we also do in our paper is like minimize. That's kind of the same problem, that forget about these rewards, just try to minimize this norm. So without constraints, just try to minimize this more in the spirit of your load balancing. That we can do as well. Maximizing a norm, I don't think.
So in a way, I can think, I mean, each round you are getting some reward, and basically that is, each round is one machine, for example. Then you are trying to
but are you then trying to maximize the maximum reward? Ooh, that. Or are you trying to maximize the minimum reward? Okay, that's actually something you could do with a softmax, but for which our techniques don't apply yet.
Yeah, what I mean is basically a norm over each round, and you're trying to maximize that particular norm. So think of, anyway, maybe it's a side question. Fine, we can talk.
But you can think of means, right? Like generalized means instead of generalized norms, like the P means.
And I'm currently working on a project where we actually are able to also, with very similar techniques, we're also getting something for maximization of means, for example. So that is in principle also possible with a very similar perspective on things. But I don't have anything I could present right now. I can only tell you, well, I feel that something is possible for those.
Yeah, like geometric means have a nice interpretation. Like they are like the Nash welfare problem.
Exactly. Cool. So, I wanted to say, in principle, we can also go beyond monotone norms. And for all we know, actually, every monotone norm. So why did I write beyond monotone norms? I wanted to write beyond symmetric norms. I think monotonicity makes a lot of sense in this load balancing problem. Assuming the norm to be symmetric maybe not always makes as much sense, or at least there are applications in which you want your norm not to be symmetric. Because online vector scheduling is an example which you can understand as online load balancing with a norm objective which is not a symmetric norm. How is this defined? Every job then causes a load on its machine it's assigned to, but in multiple resources. So what we then get is a load, for example, on the CPU, a load on the memory, etc. And then you have, eventually you'll have multiple load vectors, which is then for each machine, for each resource, you have a different load vector, which is again for an m-dimensional vector if you have m machines. And then your goal would be to minimize the following, to minimize the maximum of, well, then you have inner norms on each of these load vectors, which would be the load vector corresponding to CPU, to memory, etc. You would have a different norm. And then what we can do is actually, with just our machinery, if each of these norms has a gradient stable approximation, then we get a combined algorithm for this vector scheduling problem with this competitive ratio, where you get the maximum of these gammas and log r is the number of resources times the maximum of these of the respective alphas from your norm approximations. So for example, if these inner norms are LP norms, then each of these gammas can be log m, so for m machines, and each of these alphas can be 1, so you'd get log m plus log r. Or if you take monotone symmetric norms as your inner norms, then you'd get, I think here this would be log squared m, and these would be log m. So the interesting thing is that also here you can understand this as a composition of gradient stable norms. So in general, you'll again get a norm approximation of this overall norm. So this overall is actually a norm in a higher dimensional space. And this can be understood as a combined, as a composition of other norms, and because under composition, gradient stability is more or less preserved, well, losing these further factors, you can also, if you have these, you can use the entire proof I showed you for online load balancing, you can reuse to then also get this result for vector scheduling.
So this is matching the current best, like the Sumjin, and others.
Exactly. So this is matching exactly what was known before. I think we generalize it slightly because we could, as these inner norms would allow arbitrary monotone symmetric norms. Yeah, and I think also in terms of the techniques, it's quite similar to what they did.
So I mean, this is for like more like an unrelated machine version, but in identical machines, there is some improved bound known, like log d by log d. So here is it
okay.
Something following from this as well? Something similar bound for identical machines?
Identical machines, I don't really know, because identical machines fields, I wouldn't, so I've never thought about any of this stuff in terms of identical machines. And if one could get improved guarantees, I just don't know. Maybe one could, but I don't know.
Okay, thank you.
Cool. Yeah, then I'm already starting talking about open problems. Let me just list them here and mention them. So what are open problems? One problem is certainly to improve this O of log squared d to O of log d, or show that this is impossible for arbitrary monotone symmetric norms. So for L infinity, we know that log d is the answer. And there's no reason to believe that log d isn't the right answer for every monotone symmetric norm. What we know from our paper is that actually log d is the right answer for top k norms. Well, of course, you could do this in a more fine-grained way and take the k into consideration. Maybe then you would get something better, like what you did in LP norms. I think a very interesting question is, what if you go beyond symmetric norms? Arbitrary norms would be super interesting to see, because there are also other applications that then open up if you get results for arbitrary norms. But I also feel that it would be interesting to see further applications of what we have so far. So what I like about our result is that this has the clean interface between approximating the norm on the one hand and then just using these two properties I was showing you at the very beginning to analyze the different algorithms. And chances are you could come up with further problems for which you then just reuse the fact that there exists these gradient stable approximations of norms without actually having to open the black box again, how they work, why they work. Or also one further interesting thing is, I think, what about other input models, like things arriving in random order, having prior knowledge, maybe even offline problems. I generally feel that the techniques that we apply here could also be interesting. Very similar techniques have already been applied in that setting. But for what we do right now, I think that is still an open problem. Yeah, and that is it. Thank you very much for all these questions so far, but I'm happy to take further questions now.
Let's first thank the speaker for an excellent talk. And yeah, we can throw the floor open to questions now.
So I have one question. So if you have load balancing but divisible, not indivisible, so not integrally assigned, then do you see this techniques or the same algorithm will work? Or
excellent question. I generally feel this could work with these, but I'm not sure yet. So this is only very recently it occurred to me that it's somehow implicit here that we assume things are indivisible, and also that op doesn't divide things. So then, yeah, maybe you could reuse the proof, but I'm not entirely sure. So you might have to be careful, just because I realized,
just like chop each incoming job into like fine enough pieces and treat it as a discretized problem.
sounds reasonable.
Okay.
Yeah.
Sure.
Maybe it's as simple as that. What I was thinking about was quite the opposite of getting results for the integral problem, while actually only having a fractional, comparing to some kind of a fractional solution, and that of course turns out to be much more complicated. But yeah, if all you need is a fractional solution, probably it's okay to just think of these as tiny jobs, and then probably you can actually use the same techniques. Yes.
and for other input models like random order arrival or something, do you think same techniques might extend if you prove something?
So there was a paper by Marco Molinaro from SODA 2017 where he actually uses, for LP norms, he uses very similar techniques, or at least, morally similar techniques, to then also get results for random order. And I still hope that one could get something for random order, for example, for what we do here. I'm confident that this is possible. Then, okay, best results so far for random order always assume that the opt is large. Like this is what Marco does there. So this is something one could also consider here.
Thank you.
Okay, so do we have any other questions? Okay, so let's thank the speaker again for the excellent talk.
Yeah.
And thank you everyone for attending.
Yeah.
Thank
Thank
you.
you all for attending. Thanks.